Hello YouTube, this is Dev Physics, and in this video we will be looking at a completely mathematical derivation of Lorentz transformations. Okay, so this video will be talking about a completely mathematical discussion, derivation of Lorentz transformations. Alright, so why are we doing this completely mathematical derivation or discussion of Lorentz transformation? Will of course become apparent due to its beauty, but at the same time many of the undergrads are never exposed to this part of the structure of special relativity, because most of the time you will be talking about Michelson and Morley experiments, you will be referring to how Lorentz derived the Lorentz transformation, and later on Einstein gave the physical meaning to the Lorentz transformation. So it is of a great interest to look at how Einstein himself came up with the Lorentz transformation, and how what kind of mathematical or perhaps physical arguments he gave to actually look at how does this come about from Einstein's point of view. That's what most of the undergrads are not exposed to. So every time we read that, hey, Lorentz derived it due to protect the ether, and later on Einstein gave the physical meaning, that's not really true. Okay, so I recently found a paper on Archive by Carrol in which he talks about general relativity, and this is extremely interesting because in this paper he gives a very nice derivation to the Lorentz transformation in a completely mathematical way. So for this video you will need a little bit of tiny little bit of knowledge that you can of course get from Wikipedia or somewhere else of tensors. Okay, well, you do need a decent knowledge of tensors, plus you need a very little knowledge of group theory as well. Okay, so you need a little bit of group theory and a little bit of tensors and you'll be done. Okay, so these are the only things that you'll need. Alright, so let's begin with the video. Let's begin by, first of all, let us write down the Lorentz transformation themselves before re-deriving them using mathematical arguments. If you have two coordinate systems in this way, so that's one coordinate system and that's the other coordinate system. Okay, so that's going to be the primed coordinate system, so let's just call this x prime. This is going to be x, and that's going to be a y, that's going to be a z, that's going to be a z prime, and that's going to be a y prime. And they are separated by this distance. Let's call this r. Okay, so now if you assume that x prime, or perhaps o prime coordinate system, this is o, so o prime is moving at a velocity of v in the x direction, then the Lorentz transformation can be written as x prime is equal to x minus vt. Now this is not a video of studying the Lorentz transformations themselves. Okay, this is a video of deriving them. So I already assume that you know these transformations, so that's going to be that 1 minus v squared over c squared, y prime is equal to y, z prime is equal to z, and of course time prime is equal to t minus vx over c squared over under root of 1 minus v squared over c squared. Okay, so these are simple transformations that we have already done before, and this is what we wish to derive. Okay, so this is what we will derive. Okay, so now let's try to begin. So what we will do is we will make an assumption. So So let's just try to make the assumption. So our assumption is going to be very simple. Nature does not treat space and time separately. That's what our assumption is going to be. Now, if nature does not treat space and time separately, then we must combine space and time, and we must form a four-dimensional space, because there will be 3 of space and 1 of time, and that four-dimensional space is going to be known as Minkowski space. Okay, so four-dimensional space, which is known as the Minkowski space. And it is in this space that we assume that the distances perhaps remains the same, okay, or remain invariant. Okay, so far we have been talking about Newtonian Newtonian framework. In the Newtonian framework, the distances, or perhaps you can talk about a mathematical framework which is known as the Euclidean framework. The distances are measured in terms of space coordinates. Okay, so in space coordinates. However, when we switch to Minkowski space, we will talk about distances measured in space plus time coordinates. All right, and that will form together a distance. And we are assuming that if we switch to that particular system or that space, if we switch to a Minkowski space, then the distances must not change, because nature does not differentiate between space and time. Okay, and by that assumption, the Lorentz transformations will automatically follow. So we will look at that now. All right, so the first thing that we can do here is we can simply write down the simple infinitesimal distance formula. Okay, so distance formula that we have already studied in regular space-time, we can write down s squared, which is the distance squared, is going to be, this time it's going to be t squared. Okay, so that's going to be t squared, outside the braces of course, t squared plus x squared plus y squared and plus z square. And of course you cannot simply add the time, you will need a conversion factor, and that conversion factor is known as c, which will later turn out to be the speed of light. Now the fact that such a conversion factor exists in nature tells us a lot about the structure of Minkowski space itself. It tells us that such a conversion factor exists and it's constant, and that is a very deep insight, as we will later learn when we derive Lorentz transformation, that such a constant, the fact that it exists, right, in reality is a very big assumption to make initially. Okay, so this is just an assumption so far. This is an assumption which happens to turn out to be real. Okay, so that's really deep. And if we wish our distance to remain invariant under certain coordinate transformations, so that means that if we switch from t to t dash, if we switch from x to x dash, from y to y dash, and from z to z dash, then our distance must remain invariant. So we can write that down. Plus delta x prime squared. Let's call these are not dashes, I believe they are called prime, so we'll call them primes, and like so. And these are the that's the invariance principle that we have so far stated. So that's the invariance. Okay, so now let's simplify this particular notation to a tensorial form, because it just becomes a little simpler to deal with, and in fact we will be switching on to a metric sort of notation. We will be writing a space-time metric, and so far let me remind you that we are dealing with a flat space-time. Okay, so we are dealing with a flat space-time. manifold. Okay, so let's switch to that. Now if we switch our x's and y's to be indexed, so we must write down a convention. So our convention looks like this. This is just let me remind you, this is just a notational convention. This is nothing deep. So if we switch on x0 to ct, which is, of course, this is the conversion factor of time to space, and this is obviously has the dimensions of velocity, and you can see this is the speed of light, but so far we are not really assuming anything, because this is just a framework, right? You have to feed in 3 times 10 to the power 8 in order to make it fit to our universe, but so far it's just a framework. That's going to be x, x2 is going to be y, and x3 is going to be z. And for all simple, there's a further convention here. Further convention. The further convention is that let c be 1. Okay, so let the speed of light be 1. So now this is nothing, again, this is nothing deep. We are just switching the units. Okay, so instead of 1 second being equal to 1 meter, we are switching to 1 second being equal to 3 times 10 to the 8 meters. Okay, so that's the unit switching. So this is nothing deep. Again, this is just a change of units. And this is just for mathematical convenience. It's nothing physical. It's just a, it's just a scaling factor. All we have done is scale our graphs. So that means that this is going to go from here to x0 being equal to t, where there's a 1 again. So x1 is going to be equal to x, x2 is going to be y, and x3 is going to be z. Okay, using that. Okay, so now we can introduce a space-time metric in order to write down the distance. Remember that we wrote down this part, so let's remember this part. Okay, remember this part. Using this notation, we can write down the metric of space-time in this way. The metric can be written as, let's write this down as, eta mu v will be equal to -1 0 0 0 0 1 0 0 0 0 1 0 and 0 0 0 1. Okay, so this is the space-time metric. And using this metric, of course you have to see this, and you can look at the distance now as mu v delta x mu delta x v, and again you need to realize that we are using an Einstein summation convention. All right, so if so now the distances can be written. So what we have done here is we have written this part as this part. All right, so you need to realize that this is same as the other distance that we had written in the previous slide. Okay, so far so good. Now let's move on. Now what we wish to do is we wish to look at the metric itself, the metric, this mu v, and we wish to ask ourselves a question that under what transformation, under what coordinate transformations, under what coordinate transformations does remain invariant. So what we are asking ourselves is, what do we do to x and x prime. So if we wish to switch from x to x prime, y to y prime, and so on and so forth, what kind of transformations are needed, what particular kind of transformations will leave this metric invariant? Okay, that's the mathematical question that we are asking ourselves. Because if the metric is invariant, if the metric is invariant, it will represent the same manifold, okay, which will be a four-dimensional Minkowski manifold. So if it does represent that kind of space or manifold, that means that we have successfully employed the relativistic conditions, all right, or we have successfully converted space-time. We have transitioned from a Euclidean framework to a Minkowski framework, all right. So let's do that. Now the obvious answer to the question of what kind of coordinate transformation would leave the metric invariant, the first answer will be translations. Okay, so the first answer will be translations by constant. Okay, what does that mean? That means that if we simply have these two coordinate systems, and if we place the other coordinate system a particular distance away from the previous one, if we measure the distance between 2 points in this coordinate system as opposed to this coordinate system, they will remain the same. All right, I'm sorry for the sudden inconvenience in the video. Anyway, so what I was trying to say, what the point was, that under translations, it doesn't matter what coordinate system you use. If it's different by a constant, if it's simply displaced by a constant amount, if the other coordinate system, then still the distances remain invariant. And if the distances are the same, it will be represented by the same metric. Okay, so n mu v remains invariant. All right, it remains invariant. Now the other thing that we can possibly do to the coordinate systems is perhaps multiply it by a regular space-time independent matrix. Okay, so the second possible answer, so we write down the possible answers to the question that we are trying to face, we are trying to attempt to solve, is that the second possible answer is multiply by a space-time independent matrix. In fact, let's just call it lambda. Okay, all right, so that's a capital lambda. Okay, so this lambda is a space-time independent matrix. And by the way, before I go on to the multiplying by lambda, we can say that in here, right here, when we're talking about translations, we can write the translations as x mu prime, which will in fact be equal, it will be x mu, which will be equal to x mu prime, which equals to x mu plus a mu. All right, now again, this is Einstein's summation convention employed, and we will basically have these alpha mu's are a set of 4 numbers which are added to all these other coordinates for a translation by a constant. Okay, now again, we will be switching from matrix notation to tensorial notations over and over, so you should get used to that part. So if we multiply the coordinate by a space-time metric, a space-time independent matrix, that will look somewhat like this in tensorial notation. X mu prime is equal to mu prime lambda mu prime v x v, and again you can see the summation convention. So this is a simple column matrix, and this is a rank 2 tensor. So rank 2, or perhaps you can simply call it a rank 2 matrix. Okay, or a second order matrix. Now in a matrix notation, again, this can be written as x prime is equal to lambda x. Okay. Now what we do is, if we write the distance in regular matrix notation, the distance in matrix notation, that will be delta S squared, which will be X transpose our metric times X. Okay, so now you need to realize that this is just a matrix notation, and it is in fact the same as our metric mu v delta X to the mu, and it's not really power, it's just it's a superscript, and X v. Okay, so these both are same. This is just a matrix notation. Notation of this, okay, of this part. Anyway, so once we write that down, and the fact that we have assumed this kind of transformation, this means that the delta x will follow the same kind of transformation. This will be a delta x. Okay, so now if we switch from delta x, if we switch from these coordinates to the primed coordinates, then we can say that the problem that we are looking to solve is that delta S squared must be the same. That means that X prime transpose, that times X must be the same as X transpose X. Alright, so now if we simply switch from this prime coordinate system, we know that delta x prime is in fact equal to lambda x, and so that means that the delta x prime transpose is going to be lambda x transpose, which will be equal to X transpose lambda transpose. That will be a delta x here. That will be a delta x here. So that means that if we feed this all into this equation, that will be delta x s squared will be equal to delta x transpose lambda transpose our metric lambda delta x, that must be equal to delta x transpose our metric times delta x. Okay, so in particular we are looking for such transformational matrix such that lambda transpose the metric lambda remains invariant. Okay, so this is the mathematical problem that we are looking at. So this is our mathematical question. I know it's getting slightly complicated, but you should be used to some of these matrix notations. These are not really complicated matrix notations. In fact, these are high school matrix notations, but you might have forgotten them. So I'll remind you that transpose is in fact equal to switching the column and the row terms in a matrix. So if a matrix has 1, 2, 3, 4, 5, 6, the transpose of this matrix is going to be 1, 2, 3, 4, 5, 6. Okay, so let me just remind you the transpose. And of course, if there's a purely column matrix, then the transpose of that column matrix goes to a completely row matrix. Okay, and that's what happens. So if we have this lambda, the transpose of this times the metric, which is also a matrix, which is a tensor this time, and this might not be a tensor, times the matrix, must remain invariant. Okay, so that's the kind of problem that we are trying to solve. So let me just write this problem again. Let me write this down here. So the problem is we are trying to solve for lambda. Basically, you're trying to solve for lambda. Solve for lambda, where the equation that we are given is lambda transpose the metric times lambda is going to be the metric itself. And of course we can write that down into the tensorial notations. Okay, so we can write that down in the tensorial notations in this way, in tensorial notation. Now when I say tensorial notation, I don't mean that everything is a tensor in the equation. It's just it's a way of saying that the notation has indices. Okay, so you can write down lambda, I don't know, that's what Carrol has used, mu prime rho lambda v prime sigma n mu prime, and there will be that, so it will be a v prime. So that's the tensorial notation. So we are just looking for such kinds of lambda. Now it's a very, very cool thing to look at some analogies to this problem that you already know, and in fact those analogies will motivate us to exactly pinpoint what kind of structure does this lambda have. Okay, we can do that by saying that this lambda is basically the stuff which, well, basically this lambda is itself a Lorentz transform. So this is what is called a Lorentz transformation. And by looking at this part here, we can in fact draw an analogy with a regular SO3 group, which is the orthogonal rotational group. We have already studied in space-time rotations. When we studied this space-time rotation, we have studied this kind of structure. The fact that a rotation in SO3 corresponds to a orthogonal rotational matrix whose transpose times the matrix itself forms an identity matrix. Okay, so this is something we have studied in an SO3 group. And in fact, if you stick an identity matrix inside here, that will not really that will not really create a problem. So we can in fact do this right here, and there's an identity matrix right there and an R, and that will again result in an identity matrix. And you can see that the similar kind of thing is happening somewhere here, right? And except for the fact that this metric has a -1 factor, because remember that we have our metric which looked somewhat like this. Right, so there's a -1 factor, and apart from that, this metric is in fact an identity matrix, right? So that means that if we have an SO3 rotation that is happening, that means that this must be some kind of rotation in a 4-dimensional space, right? So if we have a rotational matrix in SO3 which is giving us an identity matrix, and remember that RT is equal to R inverse, that's the property of a rotational SO3, that will correspond to some kind of rotation in Minkowski space as well. Okay, so in fact we can look at the structure, since this analogy seems to be very good, and since the Lorentzian metric in fact only has a -1 factor which differs from an identity matrix, we can in fact say that this is some kind of rotation. So we can study this lambda as some kind of SO3 1 group. Okay, where this is a general SO3 when it comes to 3 space coordinates, and then there's one extra -1 factor which we can call a time coordinate. Okay, so this is a time coordinate. Okay, and if we say that, then we can study this transformation as some kind of rotations which occur in Minkowski space. Okay, so this means that lambda belongs to SO3 1 group, and we can study lambda under basic rotations in Minkowski space. I know this might sound a little complicated, but it's not. Okay, so it's all lambda is simply rotating the coordinate system. So instead of translating, so that's a very simplistic view of this, by the way. Instead of simply translating from one coordinate system by a constant, that's what we did. That was a solution to the Lorentz. That was a solution to lambda as well. We are looking at rotations in Minkowski space. So we are talking about a four-dimensional space. So let me remind you of that, because this is a three-dimensional structure which I'm drawing a two-dimensional board, but it's actually a 4 dimensions, and there will be rotations under that 4 dimension, and those rotations will correspond to Lorentz transformations. Okay. Now there are two kinds of rotations that we can study in an SO3-1 group. Okay, so there are two kinds of rotations. Two kinds of rotations under SO3-1. The first one is a regular rotation in space. Okay, so the first one is a regular rotation. Okay, and by a regular rotation I mean that lambda mu prime v will have this kind of structure. Okay, so if remember, if x naught is equal to time c tc, then it will have some kind of this kind of structure: 0 cos theta, a sine theta, 0 0 negative sine theta, cos theta, 0 0 0 0 1. Okay, so that's a regular space like the rotation, regular space rotation. But at the same time we have something called boosts. All right, so another one is boosts. Let me rub this down. So the other one, the other form of rotation is boosts, and these boosts form a hyperbolic function. Okay, they use hyperbolic trigonometric functions. Okay, and by the way, let me just point out that generally the Lorentz transformations are non-commutative. Okay, so let me write that down here in the corner. So Lorentz transformations non-commutative, and this obviously means that they will form a non-Albanian group. A non-Albanian group. Okay, so they are non-commutative, they don't commute, and they will form a non-Albanian group. That is general thing, so they are a part of non-Albanian group. Okay, and so now let's study the boost part. In the boost part, the lambda can be written as the boost in space and time. Okay, so now we are talking about this part here, this and the other part. So these are the two rows that we'll be talking about, and this time they will be using sine hyperbolic functions. Okay, sine and cos hyperbolic functions. So it will be a cos of phi, there will be a sine of sine h of phi 0 0, there will be a negative sine h phi cos phi 0 0, and there will be a 0 0 1 0 0 0 0 1. Okay, so this is the structure for boosts or time space rotations. Okay, so this is the space-time rotations because we are talking about the first one. This is the time row. This is the row that multiplies to the time. So this is the, in fact, this is the column which multiplies to the time. So this contains a cos hyperbolic instead of just one. So that's something that we will have to look at. So now what we do is we will actually study these boosts. Okay, so what? So let me just summarize all the stuff that we have studied. Summary. we studied that the metric remains invariant under simple translations. It also remains invariant under space-like rotations. And it also remains invariant under boosts. Okay, and all these transformations form something called a Poincare group. Poincare group. Okay, and out of that Poincare group, these two, or in fact just this part, forms a Lorentz group. Okay, and also I would like to state the fact that this part, this Poincare group, is a 10 parameter non-Albanian group. Okay, this is a 10 parameter non-Albanian group. Now let us just go through some of the boosts. Let me just go through another one. The boosts right here. So if you look at the boost structure, let's simply write down the transformation that we can have under the boosts. So you can have x prime equal to lambda times x, which will look like x mu prime, lambda mu prime, v x v. That will look like t prime, x prime, y prime, z prime is equal to cos hyperbolic of phi sine hyperbolic of phi 0 0 negative sine hyperbolic of phi cos hyperbolic of phi 0 0 0 0 1 0 0 0 0 1 times, of course, time x, y, and z. Alright, and we can write then that t prime is equal to t cos hyperbolic phi plus sine. Okay, so let's just write down x. Okay, plus x sine hyperbolic of phi. That's the equation number 1. And then x prime is in fact equal to negative t sine hyperbolic of phi plus x cos hyperbolic of phi. That's our second equation. Okay, so after this much work, we have arrived at 2 equations. And now what we wish to do is we wish to find that the fact that what is the velocity of the second frame. Okay, what kind of function the velocity of the second frame with our first frame is. Is it a constant? Is it something else? So for that, what we have to do is we have to substitute x prime to be equal to 2, because x prime is this. Okay, so x prime, y prime, z prime is measuring something here. So if we set all this to 0, we are talking about the origin of this o dash. Okay, so if we set if x prime here is equal to 0, so if we set x prime to be equal to 0, what we get is 0 equals to negative t sine hyperbolic phi plus x cos hyperbolic of phi. Let's move to the next frame. Okay, so this means that we are talking about x again. So let me just write that down again. That will be x cos hyperbolic phi will be equal to t sine hyperbolic of phi. This means that x over t, which is going to be the dimensions of speed, it's going to be sine hyperbolic of phi over cos hyperbolic of phi. That will equal to tan hyperbolic of phi. Okay. Alright, so it will be tan hyperbolic of phi. And of course we know that x over t is going to be some speed. That means that tan hyperbolic of phi is in fact equal to some speed which with which the O dash is moving with respect to O. Okay, so far so good. Now what can we do? Well, if you feed in the fact that tan phi is equal to v back into the equations that we have derived so far, these are the boost equations, I'm sorry, the equation number 1 and 2, then what do we get? Well, if you feed in okay, so let's just modify the first equation first of all. T dash is equal to what? It's equal to t cos hyperbolic of phi plus x sine hyperbolic of phi. So if we pull out cos hyperbolic of phi in the brackets, then it will look somewhat like that. This part will be t plus x tan hyperbolic of phi. So now if we let cos hyperbolic phi to be some constant gamma, and of course we know that tan hyperbolic of phi is equal to v, then we can say that t dash is equal to gamma t plus xv. Okay, so you can see that this is looking a lot like Lorentz transformation that we wrote in the beginning of the video. And of course x prime, if we pull out again, if we pull out this part, if we pull out cos hyperbolic outside from here as well, we will see that x prime looks like it looks like cos hyperbolic of phi, and it looks like x minus t tan hyperbolic of phi, x minus t tan hyperbolic of phi, which is of course v, so that's going to be a gamma x minus vt. Alright, so that looks like a Lorentz transformation, and of course by comparing it to the Lorentz equation, you know what is gamma. You know that gamma is equal to 1 over under root of 1 minus v squared over 1, which is assumed to be c, but we will derive what gamma is, okay, using this. So we will not simply compare any results, we will see what gamma is from here. So again, so let me just write down the two equations again. These are the two equations. So alright, so okay, so instead of doing that, we can simply see that we have assumed cos hyperbolic of phi to be equal to gamma, but at the same time we know that tan hyperbolic of phi is equal to v, but tan hyperbolic of phi is equal to cos hyperbolic of phi over sine hyperbolic of phi, that will be v, and we know by hyperbolic trigonometric identities that cos hyperbolic squared of phi minus sine hyperbolic squared of phi is equal to 1. Okay, there's a minus here instead of the plus, the usual plus. So if we substitute that there, this means that cos hyperbolic squared of phi minus 1 is equal to sine hyperbolic squared of phi, or you can say that sine hyperbolic of phi is equal to under root cos squared phi cos h squared phi minus 1. And if we substitute that part, okay, I'm sorry, made a mistake. This is going to be sine, and that's going to be cos. It's going to be sine h, and that's going to be a cos h. So if we substitute instead of sine h phi this part, we will get cos h squared phi minus 1 over cos h phi, that will be v, and that means that Well, if we substitute gamma in place of cos h phi, we'll get gamma squared minus 1 over gamma is going to be v, and this means that gamma squared minus 1 is going to be gamma squared v squared, or gamma squared 1 minus v squared is going to be 1, and this means that gamma is going to be 1 over under root of 1 minus v squared. And of course we had assumed initially that c was going to be 1, but there's also a c factor that comes if we assumed that c was its usual value in the usual units. And in fact these are the Lorentz transformation. Okay, so that was a long video, but we have arrived, we have mathematically arrived. So the conclusion of the video is we arrived at Lorentz transformation, at transformations, using purely mathematical arguments. Okay, and with that I would like to thank you, and thanks for watching, and thanks for tolerating this long video. But I hope that you had a deeper insight to Lorentz transformation and the fact that it can be derived using completely physical arguments, and the fact that the nature exists as a four-dimensional space, and the fact that we just assume that part leads us to these amazing transformation equations which apparently look quite complicated when you look at them for the first time, but later on when you look at them under these group theories and symmetry considerations, they look pretty simple. Okay, so they simply come out of the mathematical framework that we assumed. So thanks for watching. Please share. I don't think anyone else is going to watch the video, so there's no point of sharing anyway, but do subscribe if you wish other insightful videos from me, and thanks. Bye.